Yes, Tim, can hear you fine.
Okay, well, let me know when we start recording.
We are.
Okay. All right, so good morning, good afternoon, good evening. Thank you for joining us. As John mentioned, the purpose of today's call is to talk about how we can decarbonize, remove carbon emissions through greener combustion. Now, in our discussion, we'll highlight some of the key elements for greener combustion and how that can directly play into decarbonizing assets. For our agenda, we'll talk briefly on just decarbonization, what it is, some of the drivers behind it. We'll talk very briefly about the combustion process and how that gives us a working understanding for our discussion. We'll also talk about some of the key levers for greener combustion, followed by 4 different approaches to decarbonize combustion, and then talk about some of the environmental impacts. And as John mentioned, we have time available at the end for questions. So feel free to send your questions at any time via the chat. I won't be able to see them until the end unless John points them out. But in the meantime, feel free to enter your questions as you go, and then we can address them at the end. So the primary question is, what is decarbonization? And from a very straightforward perspective, decarbonization is simply the reduction or elimination of carbon dioxide from energy sources. And so this is an emerging trend that we see across the world, and as a global initiative that we're all moving towards. And there's a lot of drivers behind decarbonization, and those key drivers are span economic to social to regulatory dimensions. And from the economic perspective, there are decreasing cost in the technologies, in the cost of the technologies for renewable energy. And there are also a number of initiatives that facilitate the use of renewable energy, including wind, solar, or battery power. There's also carbon pricing, carbon taxes, and other costs applied to carbon pollution that you see in different kind of countries across the world. And from the economic perspective, there are some investors that are working to diversify their energy portfolio. And that comes up in different ways, but that drives the interest and demand for renewable energy. Now, from a social perspective, a number of countries and companies are working towards announcements and commitments that they've made towards net zero emissions. So net zero, no carbon emissions with their industrial production. There's also the social drivers of the global consensus on climate change and ongoing environmental activism. All of these things pushing forward the promotion of decarbonization and moving industry in that direction. And from the regulatory perspective, there are a number of policies and green plans across governments that are driving this. And one in particular is the Paris Agreement, which committed member states across the world to limit global warming by several degrees. So all of these paint the picture and provide the background for driving decarbonization. Now, from a very high level, when we look at decarbonizing combustion processes, there are 4 main ways that we can decarbonize, and that's energy efficiency, fuel changes, emission capture, and reliability. And we'll go into all 4 of these in greater detail later on in this presentation. But I just want to highlight these 4 because these are the primary focus for our discussion today. But before we dive too far into that, I do want to make sure that we're all on the same page as far as the basics of combustion. Combustion, as you might imagine, is dependent on what they call the fire triangle. Combustion requires 3 things. It requires oxygen, fuel, and a spark or a heat source of some sort. And so in order to produce a flame, you will have to have all 3 of these at the same time: oxygen, fuel, and heat. Now, there are times where you create incomplete combustion, where the fuel is not fully oxidized to carbon dioxide and water. And that can happen because of poor air-to-fuel mixing, or malfunctioning burners, or variable fuels. And basically what these 2 reactions, these are simplistic reactions, but just for our discussion, the first reaction, you have oxygen and methane reacting to form carbon monoxide and hydrogen. Those are what we call combustibles, carbon monoxide and hydrogen, those combustibles. And those intermediates will react further if enough oxygen is present. They'll react further to carbon dioxide and water if enough oxygen is present. But low levels of incomplete combustion are normal, but it can be concerned if there's high level of combustibles. Basically, you don't get the full heating value from the fuel. Now, in order to measure this, we monitor for combustion with some important measurements. Now, a combustion analyzer can measure oxygen for process control, product quality, process integrity. You can also monitor combustibles, carbon monoxide and hydrogen, for burner optimization to save fuel, to reduce emissions, which we'll talk about later, and also methane measurement to ensure safety from flame out and gas leaks. And if you're using a combustion analyzer, it's also important to measure sample flow in that combustion analyzer so that you have a representative sample from your process. So that's just a brief overview of combustion, and that will play into some of our discussion today on greener combustion. But from a very high level, when we start talking about greener combustion, let's talk about the levers associated with greener combustion. What do we have in our control to increase or decrease in order to drive a greener combustion, a combustion process with less carbon dioxide emissions? And so I just want to propose to you that there are 4 key levers for greener combustion. And in any one of these, you can use them to make adjustments to decarbonize. And I'll talk about that in a second. But just what I wanted to emphasize is that you can use fuel adjustments to reduce your carbon dioxide emissions. You can optimize your combustion process. You can reduce your oxygen set point to reduce your CO2 emissions. You can reduce the demand for heat because that'll directly reduce the amount of fuel that you use. And you can also directly reduce the emission of CO2 itself by capturing it. We'll get into all of these different approaches, but I just want to propose to you that when you think about the combustion reaction, there really are 4 different ways that you can attack and work towards greener combustion, decarbonizing, removing carbon dioxide emissions. So originally I told you that there were 4 different approaches, right? The energy efficiency, fuel changes, emission capture, and reliability. Now let's first talk about one form of energy efficiency, which is optimized combustion. And optimized combustion to reduce your fuel and oxygen set points, whatever you use for that oxygen measurement to maintain a stable set oxygen reading. So when you think about optimized combustion, the goal is to optimize or to reduce the amount of excess oxygen that you set your heater or boiler or thermal oxidizer to measure. And by doing that, you reduce the amount of fuel needed to burn the excess oxygen. Because as you add, and I'll kind of highlight that in just a second, but by reducing your oxygen set point, you have a ripple effect of reducing the amount of fuel required, to reducing your carbon dioxide emissions, and to reducing some of your other ppm level emissions. So just to highlight that, I'll give you a few more slides just to build that picture or paint that picture a little bit more clearly. In the perfect world, we have stoichiometric combustion, where we have the perfect ideal mixture of fuel and oxygen, in this case methane and oxygen, to react to form carbon dioxide and water. That provides the maximum efficiency you can have. That 100% of the carbon is converted directly to carbon dioxide, no ppm combustibles in the middle, and you have maximum efficiency. But in reality, we actually have to operate excess air. So we actually need to operate 20% excess air, 10% excess air, in order to maintain safe levels of combustion. What happens is you get low levels of combustibles, which is pretty normal, and you're slightly less efficient, at about 5.7% less efficient than the previous case. That's excess air, that's excess oxygen, and that's where we typically use. We add a little bit more oxygen and air to the process than we need. And that causes us to burn a little bit more fuel than we originally needed as well. Now, the opposite case would be to have a fuel-rich condition, in which case not all of the carbon monoxide is converted to carbon dioxide. Not all of the methane is fully combusted. And as a result, you have extremely high levels of combustibles, which is both dangerous if the process is not designed for reducing conditions, but it's also less efficient, in this case, 35% less efficient compared to the previous cases. So it's important that we operate within a safe window so that we can maintain the efficiency of our heater, boiler, or thermal oxides or fired equipment. So I just told you that we have to operate at excess air, and if 0% represents perfect stoichiometric conditions, you have a perfect 1-to-1 ratio of oxygen to fuel. As you increase your amount of fuel over time, as you increase the amount of air that you require to operate your process, the excess air on the outlet as you increase that amount of excess air, you actually have to use more fuel to heat up that excess air that's not used. Now, it keeps you safe, but it also has a heating efficiency loss because you have to heat that extra flue gas on the outlet to maintain temperature. So by itself, operating excess air has an efficiency loss. But on the reverse case, when you operate with too low, you have a combustibles loss. You have incomplete combustion. Basically, that unburnt fuel, as you get closer to stoichiometric conditions in reality, as you get closer to stoichiometric conditions, you start to see what they call combustibles breakthrough. And at that point, you have a skyrocketing effect of combustibles that are incomplete, that are not fully combusted. You have unburnt fuel exiting the stack. You have unsafe conditions. You have all these ripple effective things, and that's when you operate too low of an oxygen measurement. So the purpose of optimized combustion is to find that optimum control point, because by itself, when you monitor for oxygen by itself, O2 only, oxygen only by itself gives you a set point. So you may think to operate at 2% excess air in your fuel gas or in your flue gas. But in reality, if you had a combustibles measurement as well, you can monitor for combustibles breakthrough and find more of a sweet spot lower that requires lower fuel and that produces less emissions. So less fuel means less emissions, and it also means, in this particular case, it avoids an unsafe condition. So that's what we mean by optimized combustion. You have that optimized set point so that you're not too high excess oxygen, and you're also not too low and too high of combustibles. That was the first approach for greener combustion and a way to decarbonize combustion. Now, the second form of energy efficiency that we'll talk about is heat recovery. And heat recovery basically allows you to reduce the demand for new heat. So how can you add heat to the system so that you have? So this particular case is waste heat recovery. And in this case, think about it as adding heat back to the system. So say you preheat your air, or say you have you preheat your waste gas, depending on your process. By adding heat to the system, preheating one of your reactants, for example, you actually reduce the amount of fuel needed to heat that respective amount of air or fuel or waste gas. And as a result, that has a effect of also reducing your carbon dioxide emissions. So when I say add recovered heat back to the burner, that could be preheating the air, like I said. Other examples of waste heat recovery are waste heat recovery boilers that could be installed at the back of a thermal oxidizer, for example, to generate steam for the plant for the process. You can also use a combustion air preheater to reduce the combustion air required to preheat the combustion air and reduce fuel at the burner. So again, reducing the demand for additional heat provided by fuel by bringing heat back to the system. And if you're incinerating some type of waste gas, you could have a waste gas heat exchanger depending on the waste gas, and that will also allow you to reduce the amount of fuel because, again, you're bringing heat back to the burner, which reduces the demand for fuel consumption. So that was the energy efficiency section. Now let's talk about different ways that you can reduce in fuel, decarbonize by fuel changes. And there's two different ways that we're going to talk about briefly. The first way is transitioning to hydrogen and also transitioning to cleaner carbon fuel sources. Now, if you want to target reducing carbon dioxide emissions directly, the most apparent thing that you can do is you can change your fuel source. And in the case of changing your fuel source from natural gas to hydrogen, you completely eliminate carbon dioxide emissions. You completely eliminate carbon monoxide emissions because inherently hydrogen is a zero carbon fuel. But I will say that not all hydrogen is created equal. So as you transition to hydrogen fuels, there are different types of hydrogen terminologies that are out there. You know, green hydrogen is a hydrogen produced from renewable energy. So that could be like a biogas-based hydrogen made on site. That could be different types of renewable energy that generates hydrogen on site. There's also what they call blue hydrogen. Now, blue hydrogen is hydrogen generated from natural gas, but it also includes the capture and use of the carbon emissions of the greenhouse gases. And one of the most I guess emerging forms of hydrogen fuel and in this type of blue hydrogen production is actually through the use of steam methane reforming with the addition of carbon capture and storage and use. So that's what they call blue hydrogen. Now, if you removed the carbon capture process, you would have what they call gray hydrogen, which is just simply hydrogen generated from natural gas. And then if you generated hydrogen from coal gasification, that would be what they call brown hydrogen. Now, the costs associated with all these types of hydrogen production are very widespread, as you can imagine. But there's a lot of work to be done to make blue hydrogen more cost effective, and again, also more attention and interest and incentives for green hydrogen production. But just the main takeaway here is that not all hydrogen is created equal. Some do create more carbon byproducts than others. Now, if you're planning to transition to a cleaner fuel source, they can be carbon-based, and there can actually be an impact by going from one carbon-based fuel source to another. And so this is some governmental data on the pounds of carbon dioxide emitted per million BTU of fuel. And so as you can see, different forms of coal can have relatively high CO2 emissions per million BTU of fuel compared to geothermal or flared fuel gas or natural gas. But the biggest impact is that any change in your fuel source from high emissions to low emissions will certainly have an environmental impact. And as you can imagine, the cleaner burning carbon fuel sources produce fewer emissions. So we just talked about the energy efficiency and the fuel changes. Now let's talk about emission capture. In emission capture, if you think about our chemical reaction before, carbon capture allows you to operate just as you are currently, but it focuses directly on removing carbon dioxide from the process. And that carbon capture, storage, use, those have different emergent technologies, and that allows you to directly reduce your carbon emissions. Now, to give you some idea for what carbon capture looks like, this is a pretty helpful schematic for the overall layout. So when you think about SMR, like steam methane reforming, or if you think about just any type of stack emission, carbon capture allows you to first direct that emission either to a transport pipeline or to some type of capture source, which can eventually be used to either be used as a CO2 feedstock for other related industries in production, or that carbon source can be directed to storage, whether that be underground, offshore, in some type of or onshore, depending on maybe it'd be like underground cavern, for example. But that's just to give you a better idea of how carbon capture actually works in the big picture view of the capture, the capture point, the transport point, the source, the storage, and the use. Now, the last thing that I want to highlight is across decarbonizing greener combustion is the importance of reliability and reliability enhancements. And we're going to talk specifically about predictive maintenance using diagnostics. Now, the importance of predictive maintenance and proactive maintenance is that it reduces the need for more fuel to overcome fouling. If you think about it, like burner fouling can cause you to have to burn more fuel. Boiler tubes fouling can cause you to have to burn more fuel because there's not a good heat transfer. And so predictive maintenance and proactive maintenance reduces emissions by ensuring the cleanliness and reliability of your equipment, whether that be burner tips, like you can see in this example, where clean burner tips reduce emissions, reduces incomplete combustion, requiring you to have to burn more fuel, just as much as maintaining heater tube integrity, clean boiler, having a schedule for cleaning the boiler tubes, and also monitoring and reducing routine and non-routine flaring events, because that can be a big source of emissions that could be improved greatly through proactive maintenance, predictive maintenance, and replacing equipment when needed. Now, you can also leverage predictive analytics. And if you think about like a combustion analyzer, for example, you can have that oxygen and combustibles readings and data on hand to provide as a reference point for monitoring the health of your heater. You can monitor the calibration trends for ensuring accuracy. You can leverage the diagnostics to maintain the sensor integrity to make sure that you're getting reliable measurements. And also you can use other types of heater metrics in order to maintain the reliability and integrity of your operation. So predictive analytics provides you the data in order to make the decisions to trend reliability and ensure uptime. And altogether, that allows you to reduce unneeded fuel emissions from incomplete combustion or lack of cleanliness. So those were the 4 different approaches for driving greener combustion and how to decarbonize in different ways. Now we're going to talk a little bit about the environmental impact, and we're getting close to questions towards the end. We're getting close to the end, so start getting your questions together if you have any. But I want to highlight 3 different cases for the environmental impact of greener combustion. And we're going to start with optimized combustion. On the first case, optimized combustion. Consider a boiler, natural gas fired, has about 200 ppm of combustibles reading, and it's firing about 10 million BTUs per hour. Now that boiler by itself, before anything happens, has an efficiency of about 77.5%, operating at 3% excess oxygen. And so that translates into to 9,600 cubic feet per hour of CO2 emitted into the atmosphere. Now, when you leverage optimized combustion, and say your optimal control point in this particular heater was 1% excess oxygen, your efficiency gains goes to about 78.7%, and you reduce your CO2 emissions to about 9,500. What that means together is that you've reduced your emissions and your fuel consumption by 1.5%. So that's one way to take 1.5% off through the scenario of optimized combustion. Now the second scenario would be heat recovery. Now think about a heater, fire natural gas, 3% oxygen, 200 ppm of combustibles, 10 million BTUs per hour. Now, say the the flue gas temperature before it's released to atmosphere is about 600 degrees Fahrenheit. That's pretty hot, but there's still some heat content in there. And that system operates at about 77.5%. Say you use that heat, and prior to venting to atmosphere, prior to the stack, you preheated some of the combustion air, reducing the flue gas temperature to about 400 degrees Fahrenheit and recycling it back into the burner to reduce the fuel consumption. Now you would increase your efficiency to about 82.3%. And from a big picture, looking at the carbon emission standpoint, you would reduce your fuel consumption and your emissions by 5.8%. So that's also just reducing stack temperature, preheating air. That combination of preheating and combustion air provides additional 5.8% reduction. So a different way to look at greener combustion, decarbonizing in industrial combustion applications. Now, the last example is changing fuels. And let's say you have a boiler that's operating and demands 10 million BTUs per hour of production. Now, say the before scenario is you're operating with bituminous coal, and that generates about 2,000 pounds of carbon dioxide per hour. Now, if you were to convert to natural gas, that would directly cut your emissions by 40%, to about 1,200 pounds of carbon dioxide per hour. So just that conversion from coal to natural gas, that changing of fuels, has a significant change in emissions. And if you think about it, if you change from coal or natural gas to hydrogen, it'd be 100% removal almost, if you think about it from that perspective. So changing fuels can have a massive impact on reducing your carbon emissions. Okay, so as a summary before we take questions, I just want to reiterate some of the key takeaways. And some of the important things to remember is that decarbonization focuses on reducing carbon dioxide emissions from energy sources, as well as eliminating carbon dioxide emissions from energy sources. Anything that you can do to reduce the emissions plays into decarbonization. In addition, the combustion reaction offers a lot of key levers for decarbonization, and I'm hoping that this at least gives you some simplistic guide reference point to think about how you might be able to decarbonize your combustion process. And then when we think about the different ways to decarbonize, optimized combustion, heat recovery are ways to increase plant efficiency for greener combustion. As I showed in the previous example, transitions to cleaner fuels provide a great way to reduce carbon emissions, whether that be through hydrogen or through cleaner carbon fuel sources. And we also could use carbon capture, whether that's by itself or in parallel with SMR, steam methane reforming, in order to generate hydrogen. So there's different ways that you can use carbon capture to reduce carbon emissions, but also to support your production. And finally, as I mentioned before, predictive maintenance reduces emissions by preventing fouling and ensuring uptime and reliability. So I'm hoping that with this list of takeaways that you have at least some ideas for how you could, even today, reduce your carbon emissions and support the decarbonization across industry. Okay, so we've come to the end, and I would like to open us up to questions. So if you haven't already, please submit your questions via chat, and John will read them off very soon. Thank you.
Oh, thank you. As Tim mentioned, you can click on the chat box at the top of the menu bar if you have any questions that you do want to ask. Tim, I got some ahead of this session on email, and one question I wanted to ask you was, for a lot of end users, maybe switching to a different type of fuel is not practical or reasonable. So users are I don't want to say stuck, but using a particular type of fuel that's coal or natural gas today. And on your prior slide, you had really, I guess, two main options for greener combustion around heat recovery and optimized combustion primarily. I was just wondering if you could maybe talk a little bit about about a situation where you are basically going to be using one of the current fossil fuels, if you will. You won't have the option for greener hydrogen, and kind of how to balance the need or the desire to try to decarbonize with some of the other topics you mentioned around safety and reliability. You could just maybe talk through that a little bit.
Sure, and let me know if you have any other questions after I answer this. But I understand that I certainly understand that transitioning fuels is a business case in and of itself, let alone all of the design work around it. But what I will say is that optimized combustion is certainly one way that you can leverage your heater as is, leverage your boiler as is, to ensure fuel efficiency, ensure energy efficiency within the plant. Same with waste heat recovery, as I mentioned before. Now, with reliability, there was one article that I read that said that 70% of the flaring episodes were from non-routine events, and what a lot of those, it was a McKinsey article, and what a lot of what that particular plant did was they realized that that was a poor reliability scenario where you had non-routine flaring events, meaning that there was no intention of generating these emissions, but something happened in the process to require it. Now, in that particular scenario, they monitored for they increased their maintenance. They leveraged predictive analytics in order to prevent their operation from preventing from flare unnecessarily. Now, that could be like a big picture case of flaring, but in just general housekeeping, what I tend to think is that dirty burners generate dirtier emissions. It's clean burners that provide the cleaner emissions because you can better convert, you can better transfer heat to your tubes. You can better transfer, you can better generate a flame on your flame tips. And it's those simple things that reduce your emissions because you consume less fuel to your heat transfer process, if you will. Does that answer your question?
Yep, thanks, Tim. We had a second question come in on the chat.
Sure.
The question is, if we reduce the O2 set point from 3% to 1%, it may be risky due to safety issues. So maybe inherent in that question is just a bit around the trade-off on reducing O2 as it relates to safety. I wonder if you could speak more on that and maybe show your example.
Sure. So I'll kind of go back to my example. I think the biggest point is not to operate with just oxygen measurement, because if you just lower your oxygen set point, you're kind of blind to that low end of combustibles losses, and you absolutely want to prevent combustibles breakthrough. So it's a combination of combustibles measurement and oxygen measurement, and you obviously want to give some flexibility in your process so that you don't hit the combustibles breakthrough, but that's why optimized combustion requires at least two measurements: oxygen measurement, combustible measurement, in order to ensure safety on that back end. And you could further supplement it with methane measurement to provide that additional monitoring to ensure that you're in safe limits. But that's a great question, and that's also why we advise at least those two measurements prior to doing any type of optimized combustion. Okay.
Thanks, Tim. And I guess just to follow into that, what's the advantage of adding the methane measurement in addition to the oxygen and the combustibles?
Well, that would just provide further safety monitoring for fuel leaks and for flameouts. Because in those scenarios, you wouldn't necessarily be able to monitor for methane for unburned methane, if you will. So by monitoring with a methane detector by itself, you can also monitor for fuel leaks and flameouts during operation that could also contribute to unsafe conditions, also contribute to fuel, as I said, fuel leaks directly relates to emissions as well. So it just provides additional safety point for monitoring. So Does that answer your question, John, or should I be more
Yep,
specific?
no, that's fine, Tim.
Yeah, it's that it's an additional safety point, but it also provides that kind of back-end monitoring.
Okay.
Hmm?
Tim, I don't see any other questions in the chat. I don't know if you have any closing comments before we conclude the webinar.
Okay. Well, thank you for your time today. As you're all aware, decarbonization is a big trend within across the world, across industries, and we're happy to support your combustion process to brainstorm ways to decarbonize. I hope this webinar provided you better context for navigating greener combustion. And if you have any questions, feel free to reach out to me at tim.talent@ametek.com, or my phone number is there. So, or you can reach out via the ametekpi.com website. Thank you for your time.